Okay, I'll start. Thanks everyone for coming. I'm going to talk about Miniboxing, that's my PhD project, and how we can obtain fast generics for primitive types on the Java virtual machine. And since I'm going to use a bit of Scala code throughout the presentation, but it's still valid for Java, what I'm going to say is still valid for Java, I'd like a show of hands. Who uses Scala here? Who's familiar? Okay, so not a lot of people. I'll try to keep a parallel to Java throughout the presentation. Okay, before we start, my name is Vlad Ureche. I'm a PhD student in the Scala team at EPFL under the supervision of Martin Odersky. I've worked on program transformations, in general trying to optimize the way programs keep their data in memory. And I've worked a little bit on Scala with contributions on the backend, on Specialization, and scaladoc. Okay, these two are the logos of my projects, but we're only going to talk about Miniboxing this time. Okay, so please, first of all, stop me at any time, ask questions. I don't want to lose you. We're not a lot of people, and the presentation's flexible. I can do more or less. I just want us all to be on the same page. So really, I mean it. Just raise your hand, tell me, I don't understand that. And since I come from a compiler's background, it might be the case that I'm not explaining things very well. In some areas, I'm skipping too fast. Okay, so let's look at the outline first. We're going to see generics in general and understand what are the problems with generics right now. We're going to see what Miniboxing is, why use it, and how does it work. And we're going to conclude. So I told you already my background is in compilers, so I'm going to start with that. Compilers basically translate source code from one language, whether it's C, C++, Java, Haskell, Scala, or pretty much anything, to, I like to call it another language, because ultimately, what is assembly? It's another language, or .NET or Java bytecode. They're pretty much languages. So why is there so much fuss around languages, compilers? Well, because they actually translate something more deep. It's different abstractions that they give us as programmers to work with, and they translate them to implementations. And for example, let's take a variable in C++ or a variable in assembly. In assembly, you have to think about processor registers, stack slots, and so on. Whereas in C, you don't think about this. So C gives you a nice abstraction over different hardware components that you would have to otherwise reason about. Who of you here thinks about stack slots and registers when programming? One. Great. The problem is these are implementation details that don't help us really achieve a solution to our problem. So speaking of translating an abstraction to an implementation, if you think of Java or Scala as a sphere, what happens is that we have the Java virtual machine, which is like a flat wall. And compilers, what they do is really project this onto a wall. And not everything makes it into the implementation. One such example, generics. There are no such things as generics at the on the execution platform, on the Java virtual machine platform. So what it means is, it means that we have to somehow emulate them, to give the programmers the feeling that they're programming with generics, but behind the scenes, they would have to not have it. We would have to eliminate it. So the way the Java compiler or the Scala compiler, I'm sorry, this is Scala syntax, but it shouldn't be too hard to get, right? I mean, it's an identity method with a type parameter, takes an argument and returns it. And this argument has this type parameter we've given. So if we compile this to bytecode, what we get is something like an identity method which takes an object and returns an object, which, okay, it works. We've translated it, but it's not very good. So identity of 5, if we call it, well, Scala C or probably Java C as well, would do this. It would call identity, and it would wrap this value 5 into a Java long integer object. And this is the object representation, which is not really great. I guess, how many of you are familiar with boxing, with transforming? Okay, so pretty much everyone. Okay, so it's not really great because it inflates the heap requirements. We're allocating extra objects. I'm sorry about that. It produces garbage, which needs to be collected. And then, of course, this takes time. Values are accessed through a pointer dereference, not directly. And finally, we don't have a locality guarantee anymore, because an array of integers, we would know they're coming one after the other. Whereas an array of integer objects, they could come anywhere on the heap. We have no control over that. So what we have in Scala right now is called Specialization, and it's the work of Iulian Dragos. He had this ready around 2009, so quite some time ago. And what he did was to take this identity method and compile it to not one, so the original version with objects, but actually 10 variants of this method. 1 for objects, 9 for primitive types. We have 8 primitive types from Java, and 1 that Scala introduces, which corresponds to void. So this is how we got to the number 10. Okay, so what happens when you call identity of 5? Can anybody guess? No? Exactly. It takes the 1 for integers. So there's no boxing involved. We have versions of this method for every possible type. Great. So what if we have 2 type parameters? Well, we get 100 methods, right? Because it's a Cartesian product. For each version of 1 type parameter, you get 10 versions of the other. For the second, another 10 versions, and so on. And we do have in Scala, and also Java has functions with arity 2, so with 2 arguments. And when you have such things, you have 3 type parameters, 2 for the arguments and 1 for the return type. So that would mean generating 1,000 classes. That really doesn't scale. So a question to ask is, can we do any better than that? This is around the time I started my project called Miniboxing. And I was looking at this question. So we have a version for long. We have another version for double. We have a version for int. We have a version for float, and so on. But if you look at these closely, you can actually see that they all fit within a single long integer. So there's really no need to have all the separate versions one after the other when we can have just one. And this is Miniboxing. This is the main idea. Well, when translating this identity method, I promise it's the last time you'll see it on the slides, you get the object version of it, but you also get the Miniboxed version, which, as you can see, takes a long integer and returns a long integer. So this is sort of a version that encompasses all the primitive types. Okay, so we get 2 to the power of n versions of the method. So for 3 type parameters, we get 8 classes. I'm lying a bit here. The current implementation has 3 to the power of n. But this is an implementation detail to get the maximum performance. Ultimately, we reduce the number of versions of the class or of the method. Okay, so identity of 3, when you transform it, what you get is basically the identity m, the version that you wrote for primitives, that the compiler wrote for you. So these are all automated, in fact. And you get this int to Miniboxed conversion, which you might think, oh, that looks like boxing, right? What you would do for an integer. In fact, that's where the name comes from. It's a mini box, because we're still doing a conversion, but in fact, it's not very expensive. So in our benchmarks, we show that the cost is almost negligible. So you probably like, oh, all this compiler theory, why does? So let's look at something interesting. Why use it? And I'm going to try to convince you that this is kind of how you look after seeing this. And you'll be answering, well, for the speedups and for the performance advisories. I'm not going to tell you what performance advisories are right now. I'm going to show you directly in the demo. Before we go on to the demo, let me explain a little bit where this fits into. So, has anybody seen this paper? One person. Not a lot of people. This Reddit? 2 people. Okay. So in the Reddit, it says something that kind of hurt. If you look at the actual results, this was a paper. And the results in the paper, they said, Scala does super bad compared to all others. I wonder why. And the paper was called Clash of the Lambdas. It was a paper from last year, published by Aggelos Biboudis in the University of Athens. And it was comparing streaming support in Java 8, in Scala, and .NET, side by side. The problem, well, Scala does not have streaming support equivalent to what you have in Java 8 or in .NET. So the numbers were really impossible to compare. And in the meantime, Aggelos realized the problem and actually implemented streaming support in Scala. And this is his project. It's on GitHub. And at one point, he asked me, hey, I tried with Miniboxing and I can't get it exactly to work. It was quite long ago, but let me try to show you what happens now in the current version of Miniboxing. So, I'll open up Eclipse IDE. Can you see anything? Well, the font will be a little bit bigger afterwards. Okay, so this is the stream structure that he prepared, the stream class. And you can see it's not very simple. It's in continuation passing style, so everything's upside down, functions with strange signatures. But really, to optimize this code, we don't need much. So this is the current version without Miniboxing. And let's try to run. So here's the test, which is basically contains his benchmarks, one after another. Okay, if we try to run it, I don't think these numbers can tell you much, but let's just copy them to a file so we see them side by side. Okay, so far so good. Now, the Miniboxing plugin is already installed in the IDE, it's attached to the compiler, but it's turned off. And I will undo this right now. Okay, let's run it again. Let me first maybe recompile it and run. Okay, so do you see any difference? Not really, no. Same numbers, right? Well, what the Miniboxing plugin did was to actually give us a lot of warnings that tell us what are the suboptimal parts in the code. And they're really actionable warnings. Let's look at this one. I'm going to read it out loud. So it says the method streams.stream.apply would benefit from Miniboxing type parameter t, since it is instantiated by a primitive type. So what the compiler does is tell us, hey, look, this could be optimized, but you have to do it by hand because otherwise, honestly, I'm against automatic optimizations that change your code so much. But what you can do is just add the annotation here. And you will see there are many such warnings. But here what I'm doing is I really don't need to know the code. It just tells me in that class, in that method, you should annotate the type parameter with some annotation, with the miniboxing annotation. So I'm just going to follow what it says here. Fold left would benefit from miniboxing by annotated type parameter A. Map. Okay, the map would benefit from R. Let's do that as well. Sum. Okay. Sorry, it's a bit boring here while I add these things. Okay, timed. We can do timed as well. Or we can do add generic, because we don't want this to be transformed. Let's recompile. This one needs to be saved as well. Okay, we still get some warnings. So you can see we solved a batch of warnings, and now suddenly another batch of warnings popped up. Following code could benefit from, let's see what it says. If type parameter T, yes, I did that. And this one, it says upgrade from Scala Math numeric to Minibox numeric. Okay. Okay, so hopefully it took us some time, but it will pay off. Let's see, no more problems, no more warnings from the compiler. And let's try to run test once more. And put the numbers side by side. So what you can see is a 10x improvement in the first benchmark, 3x improvement in the second one, 30% in the third one, and something like 25% in the fourth one. So what we did really here, I basically showed you that you can obtain speedups just by following what the compiler tells you. So not only that you'll be relaxing and just without needing to understand all the performance problems, just relaxing and it will tell you where the problem is, it actually you'll be able to get really good performance. So now let's move on to the next question, which is, okay, so it's a bit of a magic thing, it's not clear how it works. I'll explain exactly what it does. There's no magic involved. So the first warning you've seen is a very simple one. You have a generic method, and you call it with a primitive type. So what Scala does behind the scenes is infer the type argument, int, and once the miniboxing plugin, when it's attached to the Scala compiler, sees this int t instantiated by int, it will say, oh, t doesn't have a miniboxed annotation. You should add it. So it's as simple as that. It will realize that you're using a method or a class for a primitive type, but you actually don't have that primitive type, that version for primitive types available. Another set of warnings comes from the fact that we can, to realize where they come from, we have to analyze the call graph. And let's take this simple example where you have a method foo calling a method bar, bar calling baz, and baz returning the value right away. So if we try to see how this works, well, we have foo calling bar, calling baz, as simple as that. What if you add the miniboxed annotation to these methods? Can anybody tell me what do you think it's going to happen? Okay, so we're going to get these methods. So pairs of the one for object, the erased version that we had previously, and the ones that are miniboxed. And what is going to happen is that you see foo calls bar, bar calls baz, baz returns. Or foo m, the minibox version, calls bar m calls baz m. So the way it will look is exactly like this. You have two separate traces, call graphs through the program, where one works for objects and one works for primitive types. Well, the good thing is that data is passed in the Miniboxed encoding, so you don't pay anything extra for encoding it. So you don't create any objects along the way. What happens if you wipe the @Miniboxed annotation from one of these generics? Well, you won't have the version of bar that is Miniboxed, right? So far, so good. Foo needs to call bar. Foo-m needs to call bar as well. So that's what it will do. But it will need to box the arguments. So it's going to warn you, hey, you know, you could add the Minibox annotation to parameter t of method bar, and you wouldn't have to pay for the boxing. And bar ideally should be able to call baz-m, so the Minibox version of baz. Unfortunately, you have to trust me on this one, it's not possible. It does not have enough information to do that. So what it will do is say, oh, I know there's a better version, but I don't have enough information to call it. Again, trying to make it actionable, how could you get that information? Well, by adding the Miniboxed annotation to the type parameter of method bar. And this is exactly what happens if you run, I put everything in an object, a singleton equivalent of a singleton in Java, with the annotation missing. And I got exactly the two warnings I told you about. So it's simply that the Miniboxing plugin, you don't need to follow all the code. It's just these are the two warnings you get. So Miniboxing tries to avoid boxing at all cost. It will try to, as much as possible, get away without having to convert to objects. And when it cannot avoid it, it will warn you. It will tell you, hey, do this and that to keep optimality. So not only that you'll be relaxing, but people are going to wonder, hey, who's that guy who did that super optimization here? And actually, you don't need to do much. You just follow what the compiler says. And actually, there's a lot more to Miniboxing than what I showed you here. But each of these items could make a talk in itself. So first of all, it replaces the library construct. So the Scala library uses specialization, and Miniboxing and specialization are not perfectly aligned with one another, so they cannot call without any overhead. So what the Miniboxing plugin does when you add it to your project, it modifies the functions, the arrays, the numeric type classes to work efficiently. Also adds interfaces to other constructs, so you run fast. And it allows you to reflect on the type parameters, which is something you cannot do directly on erased generics, on the generics in Scala or in Java. So I'm talking mostly about Scala, but I'll tell you in a second, they have something similar being prepared right now for Java 10. So this is kind of your understanding something that will help you in a few years from now. Okay, so yes, Minibox state reflection, you can ask whether you're in a Minibox class or not. Okay, so let me conclude. And this is the Miniboxing plugin repo on GitHub. If you don't see it very well, it's got 1K commits, 10 contributors. So it's not really a small project, not a big one either, but we try to make it work as stable as possible. So if you don't see this, this is from Travis CI. It's 300 tests that pass with each commit. And this is the website. It's scalaminiboxing.org. And if you want to try it out, sorry, it's in Scala again. It's not in Java. But you have everything you need there. You have tutorials. You have the way to configure the Scala build tool to use it, examples, and mailing list support to get in touch and ask questions. I have to thank a lot of people for this. And Martin Odersky, without Scala, there would be no Miniboxing. He trusted me with a crazy idea that I had with Miniboxing, let me pursue it. everybody who helped out, the Scala community, the Valhalla project architects. Valhalla project is the name of the tool, of the new direction in the Java 10 that will do specialization. And with this, I'll have one extra demo if you want to stick around a little bit longer. But with this, let's take questions, and who wants to go grab a coffee, you can already go. Yes?
Is there any reason you wouldn't want to autobox a type like that?
Sorry?
Is there any reason why you wouldn't want to autobox something?
You wouldn't want to?
So you're adding the annotations to the
Yes.
autobox. Is there any reason you wouldn't want to do that?
Oh, the question is whether there would be cases where you wouldn't want to add the @Miniboxed annotation or @Specialized annotation. Yes, there are cases, corner cases, where it actually harms performance. It probably won't happen in the JVM when they implement it on the JVM. But the two reasons I see is, one, the extra bytecode, because these are compile time transformations. So whatever they generate extra, they put in your jar file. And second, so that you don't hit one of the corner cases. So if you looked when I enabled the Miniboxing plugin, in the first instance, the numbers were slightly worse. So I think something like 10% worse. That was a corner case from the fact that you added Miniboxing, but you did not use it. And some of the constructs were already being transformed and were not compatible with erased generics. And that's why you are also getting those warnings. Yes?
Will it be included in Scala?
Question whether it will be included in Scala. I think at this point, it's going to stay as a plugin because there are too many new directions popping up. Scala is undergoing a major rewrite in a different version that will compile the same source code, but with a slightly different pipeline. And I would have to integrate it there. It's not clear exactly what the Java folks are doing. Maybe if they prepare something that maps well to Scala, we'd be better off using their implementation in the virtual machine. So right now it's not clear. It's best if it stays as a plugin and people can try it out and see what works, what doesn't. We've had a pretty bad experience with specialization in the first place because we had it in the main compiler and it triggered some problems. And people were complaining about the compiler not being stable, specifically due to specialization. So it's better off as a separate project right now. Yes?
A question towards Java. What's the difference between the bridge methods we have in Java and this kind of miniboxing in Scala?
What is the difference between bridge methods in Java and miniboxing in Scala? Well, bridge methods are there to keep the object working when you're trying to unbox when you know a type parameter is instantiated by integer, you want to unbox it. So you want to have a version. So maybe to put this otherwise, bridges are meant to keep object consistency in compiling generics with erasure. Whereas miniboxing adds bridges, but adds some additional versions of the methods in the object that directly take a long integer, a miniboxed value. So this would be the difference. And one is aimed at consistency, the other one is aimed at performance. Did I answer your question, or?
Thank you. Another question is, for example, in Java, the value of use is pools and it caches all the conversions. Have you tried this kind of micro benchmarking between the value of which uses the pools behind and this?
So the pools are being used up to 256. You can increase it. I see. Probably what you would get is not a lot well, you would get maybe faster erase generics by increasing the numbers, but you would also get a huge heap footprint, because that would ultimately mean having objects for all the integers from 0 to max int, or from minus from the smallest integer representable to the biggest one. So that would explode in your heap. You probably wouldn't want that. But I agree, you could strike a balance if you say, if you can limit the range of your values to say 0 to 2000 or to 3000, then you might be able to get away with some of the benefits of avoiding the boxing. Okay, another question?
Do you have Java version for this one that integrated with the Java compiler? Any plan for that, or just wait Java?
So I think the right answer is just wait till Java 10. They're already working, maybe to repeat the question was whether Miniboxing would be available for the Java compiler, or we have to wait until Java 10. I think it's much better if you wait until Java 10, because their solution is going to happen in the virtual machine, not in a compiler. So the performance is likely that the two will be co-optimized, and everything will go much better than if we do it in the compiler. But I do think this is a first step towards getting there. So it shows that it can be done. Another question? Yes?
The Miniboxed version of the method is the same both for long and for double. How it works in terms of arithmetic rules?
Yes, that's a very good question. What I did not show you is that aside from the untagged union, so the long integer, it also takes a tag separately that is attached to the type parameter. So it will know whether it's a long or a double or an integer or something else. And based on this, for example, if you do a toString, it will dispatch the correct version of the string. So it's not going to tell you for a Boolean false, it's not going to tell you 0. It's going to tell you false. Yes, yes. Integer division would remain integer division, because before dividing the two integers, you would convert from the Miniboxed representation to an integer, to an unboxed integer. You would do the operation and convert back. And the Java virtual machine can optimize that pattern. So in most cases, you don't have any additional overhead. Okay, I see one more question. Yes?
So how does Miniboxing work with tail recursion?
With tail recursion. How does Miniboxing work with tail recursion? It works as before. There's no change. You can still have tail recursive methods optimized. So it doesn't affect that. You might run into one corner case that I recently bumped into, but you'll get a nice error message saying, here's how you work around that. Okay, so in case you're interested, there's going to be another talk on generics that is going to cover Project Valhalla. So it's going to give you a more Java-oriented perspective. It's going to be in the auditorium. And with this, if you want, you can go, or if you want to stay for another short demo, I can do it now. So I'll let you, it's up to you. Who wants to stay in the room can stay. Thank you very much, everyone. Okay, so can I start the demo? We still have 15 minutes until the talk is supposed to be over, so okay, so this is this other example that I prepared was inspired by a Scala image processing library. And what it did in this library, the author, he basically said, in production, no single optimization proved as fruitful as avoiding boxing. And when I read that, I was, oh, but why did you have the problem of boxing in an image processing library? And it turns out the pure image library has some very nice abstractions. It generalizes over the input, the output, the way it encodes pixels, and you can basically map over images, which is pretty interesting, so I really liked it. And I took the usual approach to using Miniboxing. I coded a smaller version and tried it on my own. Well, this is what I'm going to show you, how Miniboxing works on that small mock-up that I prepared. It's hosted on GitHub as before, as the other example. And what is interesting, you have this image. I hope you don't mind the Scala syntax, but it's essentially it says this. It uses wrapper representation for the pixel, and this is another instance of a class which gives us access to read the pixels, each pixel. And you have width, height, you can get a pixel from the image, and you can map it and transform the image. So what's a generator? Well, you have a generator that, again, is generic and can take any pixel representation and knows how to create the next image. So why generics? Why use so many generics in this whole thing? Well, if you load an image from disk, you start off maybe with indexed colors, right? And then you load it up, but you don't want to keep it with indexed colors, so you'd better keep it as a 8-bit RGBA maybe. And then you transform it several times until you put it again on disk, and you get indexed colors once again, right? The problem is you do a discretization after each step, which means the colors, if they had a value in between two integers, you would convert to the lowest integer. And this produces artifacts. So ideally what you would do is keep the colors in double precision throughout the processing of the image, and only at the last step convert it back to index colors. And you get a better quality out of that. And this is where the pixel representation comes in. You can use index colors, you can use 8-bit colors, you can use double precision. It's up to you. And this is Pixel, which basically gives us access to each of the channels and can pack the color back. And all the transformations occur on double. And ultimately, everything can be stored in different formats. And we have different formats, an encoding for RGBA and encoding for discrete channels. Each channel has a certain type. It can be either a double or a float. And what I'm going to show you is a little piece of code that takes this image, and this nice image I found on Wikipedia, and adds a bit of blur, a bit of transparency, and puts these two together. And okay, so let me do that. I'm gonna close this project and start the next one. This is image example again. Let's see the test. So this is the Devox image. I'm loading it from the desktop, London, and I'm putting it in, I don't know, Devox. Done. Okay, let me run this. So ideally we should find it on the desktop at one point. You you can still see it's still running. So we got our image, our result image, but it's obviously very slow. So one thing since we have so many generics, one thing we might want to do is try to optimize it. And to do this, I will try to benchmark it. So this is just telling it to run 5 times and give me the time for each run. Okay, so let's try to run it before we change anything. It takes a while, sorry. It should take about 8 seconds each time. Okay, 10 seconds. And then it starts being faster because the Java virtual machine will start inlining and optimizing things in its own JIT compiler. Okay, so we started with these numbers. Let me put them in a file here. And once again, we enabled a Miniboxing plugin, which was turned off before. We need to recompile everything. And you already know, the first time we run it, we won't get any speedups, or maybe we'll get some slowdowns. To save time, I won't run it again, but I'll show you once again that you don't need to know what the program is doing and how it's doing it. You just see the warnings here, and we can start acting on them. So here, for example, it says the class image implementation would benefit from Miniboxing type parameter. Okay, let's do that. Okay, so then you see all of these messages. I won't spend your time adding them by hand once more. I have a little trick here which allows me to do this automatically, mark all. So I'm basically telling the Miniboxing plugin to mark everything by default. Okay, let's save, let's recompile. Still has one warning, but we won't act on this one because it's a more extensive change, so we're better off not doing it. So what you can see is pretty much without doing anything special, without even knowing what the code does, just by adding some annotations to classes, we got the 3x speed up on this library. So this is kind of the idea behind it, is get the speed ups pretty much for free. Okay, so if you have other questions, let me know. If not, thank you very much for coming.